Hello everyone, welcome to Rubber Industry NewsHour. Srikanth, Namaskar. Welcome to this weekly program for rubber industry. It's every Monday by Technobase. Today we are here for the episode number 16. Date is 2nd May. I welcome you all for this episode. Let me brief you about the what is Rubber Industry NewsHour means, what kind of content is there. Let me show you a short presentation. We'll open the presentation. And that's about the Rubber Industry NewsHour, what it is, and I'm hoping that you get a better idea. But we will not be covering every topic in each episode. We will take some topics in, on each episode and we address them appropriately. As you know, this Rubber Industry NewsHour is managed and owned by Technobase, and Technobase is a specialized organization. Let me brief you about the Technobase activities and services for the rubber industries. A short presentation to see. And that's our Technobiz. Now we have a better understanding about what is Technobiz and what kind of services we offer. Okay, now getting to our episode, today's episode, Rubber Industry News Hour, episode number 16. Let me give you quick highlights about the episode number 16. First, we'll have the market review focusing on the natural rubber market. This will be given by Mr. John Jacob, who is a rubber industry analyst. And then we have a technical talk as well as a discussion on the technology trends and practices in deflashing of rubber parts. We have a speaker from USA, Mr. Ryan Taylor, an assistant general manager of the Nitrofreeze Cryogenic service from USA. We have a moderator by the Mr. Srikanth Krishamurthy, the director of the Alfa Rubber and Springs Private Limited based in India. So these are the main components of the today's episode. And as you know, this Rubber Industry News Hour is available on YouTube at the Technobiz channel. You can always check today's episode or even in the past episodes at this Technobiz channel. Okay, let's get to today's the first session on the rubber industry market review. We have, as I mentioned to you, Mr. Jim Jacob, who is a rubber industry analyst. He's going to discuss about the natural rubber markets. Let me give you a brief intro to the Mr. Jim Jacob. He has more than 30 years experience. He's a specialist on the forecasting the rubber prices and also involved in the policy development for the natural rubber industry. He used to work for the ANRPC, shortly called Association of Natural Rubber Producing Countries, and before that he worked for the Indian Rubber Board for 23 years in various positions. Mr. John Jacob is a well-recognized and internationally known rubber industry analyst. So let's welcome Mr. John.
Hi all, welcome to Natural Rubber Market Review. Let me start with what we ended last week. So last week, we made a clear statement on the likely short-term trends in natural rubber prices. The concluding statements I made last week was this. The concluding statement was this: both supply-demand fundamental and non-fundamental factors will remain unfavorable to natural rubber markets in the short term. This was our last statements. So let us review the last week price trends against the backdrop of the statements which was made a week ago. That means we made a clear statement last week. Let us see how the prices perform during last week. So we have 6 charts. We have the first 3 charts are on futures and the other 3 charts on physical prices. So this is chart number 1, shows rubber futures traded on the Shanghai Futures Exchange. The graph is showing the period between 11 and 29 April. So the last part somewhere here shows the last week. That means the week ended 29 April. Last week, Shanghai rubber futures averaged around 12,700 yuan, which is down 4.7% compared to a week ago. Means as we projected, as we expected or anticipated, price made a marked fall. Means it fell 4.7% in 1 week compared to a week before. Then we shall go to the chart number 2, which is showing the TSR20 futures traded on the SICOM exchange. So the graph here shows the period, the price, the daily settlement prices from 11 April to 29 April. So the last week shows the performance during the week ended 29 April or last week. So during last week, prices averaged TSR20 Psycho averaged 161.4 US dollar per 100 kilogram, which is 5.7% lower compared to a week before. Means in 1 week, price fell by 5.7%. Now we'll go to chart number 3, which is showing the performance of the RSS3 futures traded on the Osaka Exchange, Japan. Here we have the daily settlement prices between 11 and 29 April. So the last week shows the towards the end shows the last week. So the prices averaged during last week at 248 yen per 100 yen per kilogram, 248 yen per kilogram, which is also down 4.8% compared to a week before. That means at Osaka Exchange also prices averaged 4.8% lower compared to a week before. So this is what this show. These three graphs shows what happened in the rubber futures during last week, and this is actually the three chart shows that the futures performed exactly in the way we expected or we projected 1 week ago through this NR market review. Now we'll go to chart number 4, which is showing the physical prices STR20 Bangkok and SMR20 Kuala Lumpur. In fact, nearly 70% of the global trade of natural rubber is in the form of technically specified rubber. STR20 and SMR20 are two prominent trading names. One is from Bangkok and other is in Kuala Lumpur. So during last week, so this graph shows the period between 11 and 29 April. This is a physical FOB prices, physical FOB prices in the two markets. In fact, last week, Bangkok STR20 averaged $164 per 100 kilogram, which is also 4.7% lower compared to a week before. And at Kuala Lumpur, SMR20 averaged 162.4, which is 3.9% lower compared to a week before. That means physical market means 70% of the rubber is traded in the form of the TSR. So in that case, rubber prices fell very substantially during last week compared to a week before. Now we'll go to chart number 5, which is giving a picture of the RSS market, ribbed sheet rubber market. We have two markets. One is RSS3 FOB at Bangkok, and the other is RSS4 local market at Kotte. In the case of Bangkok market, RSS3 FOB averaged at $215 per 100 kilogram, which is down 7.1% compared to a week before. 7.1% fall in 1 week. And at Kotte market, prices averaged $218 per 100 kilogram, which is down 1.9%. So in fact, last week we clearly mentioned that arrival of RSS improved in the auction Sundays across Bangkok, across Thailand, and because of that, we expected prices to fall in Bangkok market for RSS, and that really happened. Now go to chart number 6. Which is showing the latex prices. We have two important markets. One is Kuala Lumpur and Bangkok. In Kuala Lumpur market, latex 60% latex average $151.7 per 100 kilogram. That's a reference. It's with the reference to wet weight, and which is 3.9% lower compared to a week before. Bangkok also prices average $147 per 100 kilogram, which is down 1.8% compared to a week before. That is, two things are happening. One, supply is improving because farmers are resuming tapping. We'll come to that. That's one side, the supply is improving. At the same time, demand side is clouded because the demand for latex in the glove manufacturing industry may be slowing down because of the reopening of economies, and also the COVID threat. It is a little bit eased in, although there can be exception in a few countries. So this is what happened in the futures and the physical markets across market across countries. Now, we have seen what happened last week with reference to our prediction a week before. Now, what lies ahead? What can happen in the short term in the market, or what can happen during this week? So what are the latest developments in the supply side? Global supply of natural rubber is set to make a major increase during this week. I mean, a major increase in the world supply of natural rubber during this week, because farmers are expected to resume tapping as wintering off season has almost ended. Already a section of farmers has resumed tapping, but the majority of farmers in the Muslim dominated regions, I mean Muslim dominated region means southern Thailand and Malaysia, Indonesia, and these three regions actually is representing a major part of the supply. So in the Muslim dominated region is expected to reopen their trees for tapping after the Eid al-Fitr festival of today and tomorrow. That means after today or tomorrow, after today or tomorrow, we are expecting farmers in the Muslim dominated region also resuming tapping. Because of that, we can expect a major increase in the supply during this week, because farmers are waiting for the ending of the fasting season in the Muslim dominated region. So this will be having a major positive impact on the supply. So supply is going to improve. This is what is going to happen in the short term. And what about the demand side? Demand prospects in the short term are impacted by at least 6 factors. 6 factors. Actually, these factors we have mentioned last week. Just there is no change in those factors. Number one, the Russia-Ukraine war and the massive sanctions announced on Russia have aggravated the chaos in the global supply chain logistics and shipping delay. And more than that, the war and the economic sanctions have further escalated the shipping and logistic costs, which were the shipping and logistic costs were already high, and the war-related issues have aggravated the issue, or I mean, there is a further escalation in the logistic cost. And second factor, auto sector is impacted by the continuing chaos in the chip semiconductor shortage. Third factor, manufacturing activities world over are hit by overheated inflation, high raw material prices, and supply disruptions, growing uncertainty and volatility. So there is a cost of when a business has uncertainty and business has some kind of a volatility, there is a cost of that. There is a cost of that. So at the moment, world over manufacturing activities, I mean business activities in general and manufacturing activities in particular, are impacted by growing uncertainty and volatility. In addition, there is a high inflation, high raw material prices, and supply disruption. These are also impacting the manufacturing activities world over, and that will have a negative impact on the global demand for natural rubber as well. Now, then fourth factor, global economic outlook has been downscaled by the IMF. As I mentioned last week, IMF on 19th of April scaled down the outlook for 2022, global outlook for 2022 to 3.6%. Just 3 months ago, that means in just 4 months ago, that is in January, the prediction by IMF 2022 forecast by the IMF was 4.4%. So the 4.4% anticipated for 2022 has been scaled down to 3.6%. So in fact, rubber demand is directly linked to the global economic growth. So this downscaling will have a negative impact on the global demand for natural rubber. Fifth factor, manufacturing in China is disrupted by the continuing COVID lockdown in Shanghai and several other parts of China. This is a major factor because China is accounting around 43% of the global demand for natural rubber. So whatever happening in the Chinese manufacturing is crucial for the world demand for natural rubber. As for the data released by the China on 30th April, factory activity contracted means there's a shrinkage in factory activity or manufacturing activities in China during April, and this is a second month that Chinese manufacturing sector is shrinking. And at least then I would like to add that, so at the moment manufacturing activities has contracted to the lowest since February 2022, lowest since February 2022. Lowest since February 2020. China, so we have to consider that China is world's second largest economy, and also China is contributing for nearly 43% of the global demand for natural rubber. And the sixth factor impacting on the demand prospect for natural rubber is that China's slowing manufacturing is not only impacting China, but it is impacting the manufacturing activities in other Asian countries, because other Asian countries are actually depending on the China's demand. So whatever happening in China will have repercussions in the manufacturing activities in other Asian countries. Other Asian countries, I mean Japan, Taiwan, Vietnam, Malaysia, and several other countries. For example, Japan's manufacturing activity grew at a slower pace from the previous months in April. Supply chain disruption and a strict Chinese coronavirus lockdown are hurting Japanese overseas demand. So that means we have just reviewed what is going to happen in the supply side, and we have made some observation regarding the demand side. In short, I would like to state that supply demand condition is likely to remain unfavorable for rubber prices in the short term. At the moment, supply demand condition is unfavorable. Now we have reviewed the supply chain supply demand situation. Now what about non-fundamental factors? Apart from supply and demand, there are a number of factors impacting on the prices, influencing the prices. The most important development in this regard, I mean the non-fundamental sector, is the US Federal Reserve is going to have a policy meeting during this week. And at this week policy meeting, US Federal Reserve is set to raise interest rates by a bigger than usual 0.5 percentage points. So sharply higher food and fuel prices lifted the overall inflation, US inflation, to a 40-year high of around 6.6% in March. So this is putting pressure on the US Federal Reserve to revise up, to raise the policy interest rate more than 0.5 percentage point. And the speculative investors are awaiting signals from Federal Reserve Chairman at his post-policy meeting press conference. The press conference is expected to disclose the future path of interest rates. And the prospects of higher US interest rates increase the opportunity cost of holding riskier assets and portfolio. If interest rate is high, that means the opportunities of holding riskier assets is higher. So the higher interest rate makes speculative investment economically less attractive. So what is the outcome? What is going to be the outcome of the US Federal Reserve's policy meeting during this is crucial for not only for commodity market, not only for the equipment market, for all speculative investment. This is crucial, and rubber market is no exception. Then another non-fundamental factor, the benchmark 10-year US Treasury yield currently rolled at multi-year peak. The US Treasury yield is currently rolling very high. So higher bond yield keeps speculative investors away from commodities and equities. So they have one sector where the growth potential is high. So usually speculative investors will be attracted to to that particular sector. Then we have also seen the last week we have seen equity market world over making huge fall last week. This was largely because of the disappointing quarterly earnings of the companies. So because of that, there was a major downswings in the global equities and stock indices during last week. For example, in April 22, the index S&P 500 index suffered its biggest monthly fall since the onset of coronavirus pandemic in the early 2020. So that means S&P 500 last week suffered its biggest monthly fall after the coronavirus outbreak. Then, but not only that, S&P 500 tumbled 3.6% on last Friday, 3.6% fall in a single day. And this is the biggest one-day drop since June 2020. And another index, NASDAQ, posted its largest monthly drop in April 22 since 2008 financial crisis. That means non-fundamental factors also stay unfavorable to rubber markets. So, putting it simply, demand supply situation is expected to stay unfavorable to rubber prices in the short term, and non-fundamental factors are also likely to stay unfavorable to rubber prices in the short term. This is what is expected. So that means next week we are not expecting a recovery in rubber prices. At the same time, we don't expect a major fall in prices because at the moment rubber prices are rolling at a rock bottom level. For example, Shanghai futures market is rolling around 12,700. So there is no space for falling down. So we are not anticipating a further down in prices, but we are expecting prices. We don't expect a recovery in rubber prices, or roughly we can say that prices are likely to stay, means almost stable, or maybe it is moving sideways in the coming week. That's all. Thank you very much. See you again for the NR market review next week. Thank you.
Thank you, Mr. Jim Jacob. And that's the natural rubber market review. I'd like to inform you all of you that Mr. Jim Jacob is also giving a master class on the natural rubber economics. If somebody is interested in the ins and outs of the economics of the natural rubber industry, you should consider to join this master class on the 15th June. It's an online program. We're also having the Natural Rubber Dialogue, NR Dialogue, which is a monthly program in cooperation with the Jim Jacob. We're having this every month on the last week of the last Thursday of the month. The next episode is focused on the Philippines rubber. We have three eminent rubber industry professionals from the Philippines are sharing their inputs on the challenges and opportunities in the Philippines natural rubber industry. So free to join. I welcome you all to participate. Now, before we get into the next session, let me give you an overview about the rubber industry upcoming events. First, I'd like to introduce about the World Rubber Summit. It's organized by the International Rubber Study Group, IRSG. They're hosting this program during the 24th to 26th May in Singapore. For more information, you check at the rubberstudy.org. There is a next event in Malaysia. This is IRICE, International Rubber Industry Convention Expo. It's organized by the Malaysian Rubber Product Manufacturing Association during the 6th to 8th September at the Kuala Lumpur Convention Center in Kuala Lumpur. Let me show you a short presentation on this exhibition. Malaysian exhibition, Rubber Expo. There is an event in India, IRC 2022, which is scheduled on 24th to 26th November in Bangalore, organized by the Indian Rubber Institute. You can check more details at the irc2022.com. These are the Technobiz exhibitions which are scheduled in 2023. The GRTE, Global Rubber Latex and Tar Expo, scheduled on the 29th to 31st March. And we have an Arab Rubber Expo scheduled in October. The date is yet to be finalized, but located in Sharjah in United Arab Emirates. So these are the upcoming events. There are many other events. You can check your online. And, please participate. I'd like to give you some info on the Technobiz Rubber Technology online training program. I'd like to emphasize here, Technobiz is probably the specialized online training provider for the rubber industries with huge resources under the platform called NewsHour Webinars. You can check the details, knowhow-webinars.com. We have more than 40 well-experienced and knowledgeable experts as a resource person providing very specialized training programs, online training programs for the rubber industries. We have three types of programs. Short versions, it can be 30 minutes to 3 hours long. We have developed 250 plus short topics. We're still working on many other topics. Hopefully we reach out to the 500 plus focus subjects for the rubber industry. And we have master classes, which is 1 day to 10 day long on various subjects, 20 plus master classes already. And we also offering the 3 months diploma program starting next year. So welcome you all to check the details of all these subjects at the knowhow-webinars.com. We are specialized in offering the online training program for the rubber industry. Okay, the next session is the Rubber Industry Tech Talk. In Rubber Industry Tech Talk, the focus is on the technology trends and practices in deflashing of rubber parts. This is basically not just a technical presentation, but we also have a discussion. It's a combination of presentation as well as discussion. We have a speaker next specialized in the deflashing cryogenics, Mr. Ryan Taylor, working as the Assistant General Manager at Nitrofreeze Cryogenic Services based in USA. He has more than 10 years experience in the rubber and plastic finishing industry with the project management, technical sales, and operational roles. His role at Nitrofreeze includes developing a new business, account management, marketing, and overseeing day-to-day operations at the company. He helps develop a new process for deflashing and deburring molded and machined parts. So it's good to have Mr. Ryan Taylor. At the same time, we also have Mr. Srikanth Krishamurthy. He's moderating the discussion and also participating in the technical discussion. He's the director of the Alfa Rubber and Springs Limited. He's been working as a director for I think close to 30 years. Alfa Rubber produces the automotive and engineering rubber products. They also specialize in producing the foam and felt components for the NVH applications. They are supplies to OEMs, Tier 1 and Tier 2 vendors. So we have two specialized and two people with a huge experience in the deflashing. So welcome them for this session. First, I invite Mr. Ryan to make a presentation on the technology trends and practices in deflashing of rubber parts. Ryan.
Good morning, or good evening in that matter. I know it's a different time all around the world, and we've got quite the audience. So my name's Ryan Taylor. I'm with Nitrofreeze Cryogenic Services. Today I'm going to be presenting technology trends and practices in deflashing of rubber parts. So the company I work for is Cryogenic Institute in New England. We trade and sell under the brand Nitrofreeze Cryogenic Services. We're located in Worcester, Massachusetts, which is about an hour outside of Boston in the United States. And we offer a boutique of cryogenic solutions for the manufacturing industry. So the company was started in 2002, and we've expanded significantly since that time. The company was created by a technology transfer and originally created to provide cryogenic treatment services for metals. So that process in particular would be to enhance the properties of metals, including tool steels, aluminum, and other exotic alloys. And as we grew and prospered, we added additional services. We actually offer the most services for cryogenics under one roof in all of North America. I mean, and those include deflashing, deburring, cryogenic treatment, dry ice blasting, and many others. As for myself, I started with the business in 2007 as an intern. I actually used to shine shoes for the owner at his country club that he would go golf at. So that's where I met him. That's where I got started, and started marketing and sales, and ended up continuing to develop the business and develop new accounts, and then moved more into operational roles and management roles. So it's been quite the ride over the past, I ended up leaving and coming back. It's been quite the ride, been a good time. Learned quite a bit here. So I wanted to introduce some of the services that we provide the rubber industry. One is dry ice blast cleaning. It is environmentally friendly. And what it does is it removes, surface contaminants from molds so that you don't have to, take the mold down out of the machine and take it apart and clean it. Instead, you can simply blast it with dry ice. It's using compressed air and dry ice to blast at high pressure to remove any surface contaminants. So, if you have like mold release agents or, built up rubber in a mold that you've been running for days or hours, or, you just have it's a problematic mold, it will work to clean it and remove those surface contaminants. So the beauty of it is that you can do it both in the press. You don't have to send it out to be cleaned. You don't have to take a toothbrush to it, and you don't have to take a ton of time to clean it. So it increases your uptime in running your molds. And this is a video to show you. And there you go. So that's dry ice blast cleaning in action. Now, the other thing we offer for the molding industry, in particular with rubbers and tools, is cryogenic treatment for metals. So there's 3 transformations with that. One is residual stress relieving. So any stresses or propagation lines that would be in a steel, for example, as you machine it, you can induce even additional stresses. So what we always recommend is that you cryogenically treat your tools after you've done machining. You also benefit from crystalline structure modification. So what that is it's increasing the durability of the metal in particular. This process reacts very well with steels, and you're also going to benefit from wear resistance improvements. So any pins in the mold, any slides, anything, any moving parts, where you're going to have 2 metal surfaces coming together, you always have the potential for wear there. This is going to drastically improve those, the lifetime of those parts. So overall you end up with parts that are going to last longer. That's what I always tell customers. So great, you can definitely increase the life of a mold by doing this, usually anywhere from 25 to 50%. And now into the bread and butter of our business, and where we see the most opportunity and what we do the most of is cryogenic deflashing. And this is, an efficient means to remove excess molding flash created during the molding operation of parts, whether it be compression molding, injection molding, even sometimes castings, anything like that, where you have residual flash, you have excess material, where parting lines come together, gate vestiges, those sorts of things. This is a great process to remove it. And one of the best parts about it is the fact that not only is it offer a consistent result, because we're not doing parts one by one. We don't have people doing them by hand and having different, you have that human variable. You're removing that. So you have a batch process that's removing flash, and the way it does it is by both tumbling the parts and also blasting them with a polycarbonate media. That's one way of doing it. There's also cryogenic tumbling, which is very similar. It's still a cryogenic deflashing process. In that process, you simply have parts being loaded into a chamber, and the chamber is rotating at a very cold temperature, which is different, part to part, and I'll get into that. But ideally, cryogenic deflashing is working for more than just rubbers. I mean, it works on plastic parts, works on elastomeric parts, and then even some metal parts like die casted and metal injection molded parts. So, ideally the reasons with certain materials, especially like, for example, like a silicone, it naturally flashes and you end up with tear trim, and cryogenic deflashing will remove that. For other tools and parts in particular, quite often we hear, hey, let's just fix the mold. And that's okay if the mold doesn't require a lot of repair. However, if the mold is not, is towards the end of its, lifetime, and the part, there's no need to, or the money isn't there to purchase and build a new mold, this is a wonderful process to extend the life cycle of that mold and finish out the entire part's life cycle. So you're removing, again, parting line, gate, gate vestiges, and ejection pin flash. And one of the things I really want to cover with this presentation today is the fact that, when you're starting a new process, and in particular a new part, we want to go over what it means to develop that process, because there is some trial and error in it, but there is also some very basic fundamentals that have to be reviewed, that you can almost build a database so that let's say you're running, 75 or 100 different part numbers, and you're running certain materials, let's say EPDM rubber, a butyl rubber and a silicone. There's basic things that are going to come into play that you can take the trial and error out of your deflashing parameters. So I always say start with the basics. You've got part geometry and physical features. If you've got a part that's flashes simply on the external, the exterior of the part, then a process like cryogenic tumbling will work just fine. Because you've got parts in a basket rubbing against one another, and then they're also tumbling. That will remove the external flash. Now, if you have a part that has flat, let's say you have, some special kind of gasket that has flash both on the exterior of the part and the interior of the part, well, that's where like a media blasting process would work very well. Not only because again, it's tumbling and it's blasting the media. So that's going to remove the flash both on the exterior of the part and the interior features. Then we have material. Material is another, fundamental thing, is going to require different temperatures at which you run. So over the time, we've developed a database. We've run thousands of different part numbers, probably tens of thousands at this point, and millions of parts. Probably even maybe even 100 million at this point. We do quite a bit. So we've created a database essentially in Excel where we have different, we're able to search by material type, and we're able to create, basic guidelines as to what temperatures to start at. And I'll get into that further along. But again, another thing, flash characteristics. Interior, exterior, thickness is very important, because that's going to determine what kind of media you run. And it's also going to determine, which process you're going to use. Again, going back to where is it located on the part. So those fundamentals, again, will determine your batch size and your temperature and your media type, and ultimately even looking at it from even further back, which process is best for the part. So deflashing variables. In this slide in particular, I'm going over with the media blasting, because that is the majority of what we do, because we do so many different parts for so many different clients. We need a process that is all encompassing. We'll remove the flash from virtually any part, whether the flash be on the interior or the exterior. So that's the process we use. We do have cryogenic tumblers in house. However, the majority of what we do is with cryogenic media blasting deflashing. So first is time. Time is going to determine how long your cycle is. Next, you have temperature. Again, what temperature are you going to be processing the parts at? It can range anywhere from, freezing to, we've gone down as low as like negative 200 degrees Fahrenheit. Then throw wheel speed. So this is the rate at which the media is blasted at the parts. And that's, in our revolutions per minute. And then we have tumble rate, another metric in revolutions per minute, and that is at the rate at which the basket rotates. Next, we have type of media. Depending on which process and which equipment, whether it be cryogenic tumbling or it be cryogenic media blasting, you have different types of media. So these all come into play, and we refer to these as the 5 T's. Next, we have total cycle time. So total cycle time isn't simply when we process something from a costing point of view, and this is, if you want to go quote a customer a part and you're going to have to cryogenically deflash it, you have to look at the cycle time in all encompassing, because it's not just a matter of, okay, yep, we put the parts in the basket and then it gets down to the temperature and it runs. No, it's beyond that. So, loading the parts, we have to load them in a basket. We have to then put the basket up into the cryogenic chamber in the machine. And then we have a cool down cycle. Parameter. And what that is basically when you open that door, although it's a gaseous nitrogen atmosphere, the temperature will start to go back up to room temperature. So we try to keep that door closed when we're putting the basket in and do it very quickly. So you have to cool down. So let's say we start at, around freezing. So say 32 degrees Fahrenheit. We go down to negative 180 to run a silicone part. Well, that is a matter of, that can be seconds, it can be minutes. It's based on every piece of equipment is different. For us, a cool down cycle to negative 180 degrees Fahrenheit could be a minute. Then we have the blast cycle. So this is when the basket is rotating in the machine and being, blasted with media. So that can range, it can be a couple minutes, and then it can be, up to like say 10, 15 minutes. And if you're using a cryogenic tumbling process, it can be even longer, depending on your batch size and that. Then you have the post-tumble. So the post-tumble is simply now the media has stopped blasting, but the basket's still going. And the whole point of that is at that point, gaseous nitrogen is shot in with compressed air as well to remove any residual flash left on the parts and to remove any residual media that might be in the basket. And then we have unload, and that's simply taking the basket, opening the door, taking the basket out of the machine, and putting the parts into a work holder of some sort so that they can be brought back to ambient temperature. That's your total cycle time. And unlike, a vibratory deflashing process or something else, it's minutes, it's not hours. It doesn't take hours to do this. And next, when you're determining cycle time, multiple variables, will come into play. When we start a new part, first things we look at before we go ahead and say, yeah, this is going to be 5 minutes, this is going to be 10 minutes, we look at the part geometry. Okay, so when we're running samples, we always say more the merrier, because if I run one piece in a basket, that is not going to be representative of my of what I can do efficiently. And it's not going to really help me quote out a process either. So we ultimately like to get in, for example, a box of parts, and we like to do some experimentation, but that allows us to get a good feel for the batch size. And a pretty good rule of thumb is, and we use part counters to determine this, but is to basically cover the bottom of the basket. And even then, our basket's about, say, 18 inches tall. We could go, with certain parts up to, say, about 6 inches worth of parts. And then again, residual flash characteristics. As the part got flashed, and tear trim, if it's got tear trim, well, that's going to be a longer cycle than, say, a part that just has, 2 or 3 thousandths of an inch of flash. So what we always recommend when we're creating a new process is to start short. You don't want to go and say, yeah, let's do this for 15 minutes, because you can always run it for a couple minutes and then add a couple minutes and do it in small increments. You don't want to just dive in and say, yeah, let's do it in 5 minute, 5 minute intervals. The idea is to start, with a short cycle, couple minutes, add them in, the additional minutes in, as you go. So you run the parts, pull them out, take a look. Okay, the flash is getting removed, but there's still residual flash. Put the parts back in, run them for another couple minutes, take them out. You either have, maybe at this point, have achieved what you're looking for. You might need a little bit more time. But at the end of the day, whether it be cryogenic deflashing with the media blasting or it's cryogenic deflashing with the tumbling, your cycle should be well under 30 minutes. If they're not, then something is amiss, whether it be, it could be temperature, or it could be, other factors and variables come into play. So next we have temperature, being one of the very large fundamentals of what we do. The temperature is going to ultimately make the flash, at what, these cold temperatures is what's going to make the flash brittle enough to be removed. But we don't want to make the parts almost frozen through, because if they do, then they have the potential for breakage. They also have the potential to, you can almost maybe, start to really beat that part up, and you don't want to do that. So in terms of what temperatures we process parts at, we're between -30 and -200. And to give you examples, in terms of ranges, this is where you should run your parts. You should start, I always like to recommend to start on the low side, see if you're getting a result. Usually what I find is, with the temperatures, for example, polymers is -50 degrees Fahrenheit to -100 degrees Fahrenheit. Well, we could run, let's just say a nylon at -70 degrees Fahrenheit, while a peak might be run at -60 degrees Fahrenheit. So I always recommend to start on the lower side. Next, we have elastomers. We run those between -100 degrees Fahrenheit to -150 degrees Fahrenheit. And then silicone, that is the material that we process at the lowest of temperatures with the deflashing process. And that range is -150 degrees Fahrenheit to negative 190 degrees Fahrenheit. And again, you want to start on the low side. And what I recommend is you don't, in terms of temperature, do it in increments of 10 degrees Fahrenheit, and go colder as needed. But I usually find that, a lot of it has to do with geometry again. So like, if you have a small O-ring, you could run at, negative 170 degrees Fahrenheit. Well, if you have a larger part that is thicker, you would probably run that silicone part closer to negative 180 to negative 190. So this is where geometry comes into play with temperature. Next, we have throw wheel speed. So this is a function of media blast deflashing. You're not going to have a throw wheel in your cryogenic tumbler. What the throw wheel is doing is it's drawing media up from a hopper down underneath the cryogenic chamber, pulling it up, and then blasting it out. And this range is, for the speed is 5,000 to 20,000 RPM. And that can vary machine to machine. With the equipment we use, which is by CDS, that is the range. And that range and speed is going to be determined by, part geometry, thickness of the flash, and your batch size. If you were to run at, a very low RPM, what you're going to find in a lot of older equipment, I've seen this, is that a lot of the throw wheels will only go up to say, 10,000 RPM. And one of the issues with that is that it takes longer to deflash. I mean, ideally, at the end of the day, we want to do this efficiently, and it's to ultimately make money. So speed, what we find is there's a sweet spot. And that sweet spot is usually, if you're, let's say your throw wheel speed, range on your machine is 5,000 RPM to 10,000 RPM, it's good to start in the middle. With our machine in particular, we've got 5,000 to 20,000, so we're right around 12.5. That's where we like to start when we're doing samples. Ideally, what I've found is at the very high end of the spectrum, like let's say, if you were running near 20,000 RPM, there is the opportunity, and it's not a good one, to remove flash, but also start to chip away at the part. So that's something you want to avoid. So it's always good to kind of start in the middle and get, you can get more aggressive as you go, but add like say 1,000, RPM on that as you go. That's what I would recommend. Thickness of flash is going to be very tremendous in this. If you've got a part with tear trim and the tear trim is several thousands thick, yes, you have to run it, at a higher speed. So thinner parts, I always recommend, again, to go in the middle, run your thinner parts. You're probably going to find your with our machine in particular, you'd be sub 15,000. If you've got a part that's thicker, with thicker flash, a larger part, you can go higher. Next, we have tumble rate. And that is essentially, the basket, again, tumbling, and the parts within the basket at the bottom of the basket tumbling against one another. Okay, so that tumbling function is largely what removes the external flash from the component being processed. And this range is anywhere from 5 to 40 RPM. With a cryogenic tumbler, it's usually lower. But I mean, all machines are different, and there's probably, easily at this point, when I started, there was probably about 6 to 7 suppliers of cryogenic deflashing equipment that I personally knew of. Today, I know of roughly 20. So, I mean, it's expanding, and the technology is catching on as it has moved from simply being able to just process rubber parts to also being able to process plastic. So it's, gaining momentum. More people are learning about it, and, even bringing this equipment in their facilities to, complete the flashing processes. So, with this, especially with media blasting, the idea is you don't want to have a super high tumbling rate with a media blasting machine. What you want to be able to do is remove the flash from the parts via tumbling, but anytime you're using media blasting, you want the media blasting to do majority of the work. It should be like, I would say something like 3/4 media blasting, 1/4 tumbling. So we find that our best results are, at the low side on this one, and that way the media does its job. So we're usually somewhere between 10 and 20 RPM on the tumble rate when we're processing parts. Again, even when you're using a cryogenic tumbler, you should probably also start at the low side. You don't need, I find, around, say 10 RPM, there's a speed on that one. So you probably want to run that at like somewhere around, start at about 25% of whatever your total power is, for your revolutions per minute on that kind of machine. Next, we have type of media. So there, in the past, have been other medias, but for us in particular, and what I've seen the industry do here in the United States is anytime we're using media blasters, there's cryogenic grade polycarbonate media. And you can see this in the picture, different sizes, they range from 15 thousandths of an inch to 60 thousandths of an inch. The majority of what we do is somewhere between 15 and 30 thou. The 45 and the 60 thousandths of an inch media is used more on what I found machine parts, hard plastics. I find that when we do, if we were to run, say a rubber part in particular, you're going to run into problems. Just because what ends up happening is the media will chip away where the flash is attached to the part. So using a smaller media will remove the flash, but it's not going to induce any damage. It's not going to start chipping and eating away at the part. So the bulk of what you want to do is somewhere between 15 and 30 thou. And that's going to be largely dictated again by part geometry. We deflash parts with very thin passageways, sometimes with cross holes. And what happens is, we have to make sure, we always look at that and say, okay, well, we're not going to use a media that is going to get lodged in there. It's just something to be aware of. Next, we have triangular polyamide, and that's used in tumblers. And that can, that comes in triangles. There's also, I've seen spherical ones as well. So, there are different shapes available, but for the most part, if you're doing cryogenic tumbling, I find that the triangular polyamide works the best. That's been our experience. So next, selecting the media type. I've got a part over here. This is an EPDM rubber part. It's got flash on it. It's got tear trim. The flash isn't that very thick, but the tear trim is. So on a part like this, this is where smaller media would come into play, especially with the edges of the part. It's got, raised features. We don't want to batter those down. So we would run, again, a smaller media. And in a part like that, you're going to start, if we were to start that as a sample, we would process that either with a 15 or a 20 thousandths media. And we have several machines. So what we tend to do is, we don't like to always switch out our medias. You can do a machine changeover during the day multiple times and we always recommend to start with the smallest media and work up in size of media as we go through the day. So let's say more often than not, we start with a 15 thousandths media. Run whatever parts we need to run with that, then move to a 20 thousandths and so on and so forth. But that way you can try, parts with a 15 thousandths media, and you can also try the same part with a 20 thousandths media. And if you get the same result, well, then other, variables come to play, like time. You could run, what the same process you might run with 15 thousandths media, you know, could be shorter in periods of time, you know, for the total cycle if you were to run a 20 or a 30 thousandths media. So again, always good to start small, and it's always good to make sure that, you know, you try a couple different processes, because ultimately, if we're going to deflash, let's do it efficiently, and let's, you know, maximize our machine time so that we can continue to process parts, because bottlenecks are not a good thing. You know, and with geometry, like anything, if you've got a part that's like a cylinder and it has, you know, a thin section running through it, or, you know, slits like that, you want to make sure the media is not going to get stuck in it. That's imperative. So anytime you have, like, let's say, just for example, if we had a 60 thousandths of an inch passageway, we always will start, we wouldn't even think about putting a 30 thousandths media in there. It would definitely get stuck. I mean, it would probably build up in the part. You know, because I mean, this, you know, media is being blasted at significant speed. It could get stuck, and then it builds up, and then the parts don't get deflashed. So smaller is better with something like that. That's something to keep in mind. It's very important when you're selecting your media. So advantages of cryogenic deflashing, and I always compare it to, you know, more labor-intensive practices. I can't tell you how many manufacturing plants I've been in and walked in and been shown a deflashing cell, and it's essentially, you know, usually people with very small hands that are able to, you know, have quite a bit of finesse, and they are deflashing using, you know, X-Acto blades and razor blades and special knives to, you know, remove flash. And the issue with that is you've got, again, multiple people around a table, and they all have their own style, and some are more aggressive than others, and some have more finesse than others, and some have done it for, you know, a couple months, or they're brand new to the job, and then you have some who have been doing it for years. So there's issues there. You know, there's that human variable, and this process is largely going to take that out of it, out of the deflashing process. You're going to, you know, put a batch of parts into a machine, process them. Granted, you do have a human operator. With our media blasting machine, we're able to literally program the system by part number, so that every time we run that part, all we have to do is input a part number. And once the parts are in the basket and the basket has been loaded in the machine and the door is closed, we can hit enter and run that process time and time and time again. Because it's quite often that, you know, we don't run this part for, you know, it could be a month, it could be a day, it can be years. Sometimes we see, you know, we don't see parts for years. So we save all these records in multiple places in a database, but we also save it on board the machine. So you're going to get consistent results. You've got a batch process, you're saving the process, you're recalling the process time and time again. If the molding process doesn't change, so if we don't have a major issue that arises with the tool in particular that's being run, we're going to get consistent results. Sometimes what we found is, you know, as tooling wears, there is the potential, you know, to have to increase the cycle time. But for the most part, the other variables remain the same. You've got fast turnaround. Again, we don't have people removing the flash by hand, sitting around a table and doing it all day. I mean, you know, you're talking so many parts per hour that these people are able to process, parts per shift, however you want to look at it. You know, this is going to allow you to process astronomically many more parts in a day than they would by hand in the same amount of time. I mean, I can give you a recent example where we had a customer who was taking something like 30 minutes to deburr a very, very intricate part. and they were doing it by hand, and we were able to essentially if we looked at the time spent to we were able to process in that same amount of time, instead of one part, per person, we were able to process 1,000 parts in the 30 minutes. So significant advantage there. Next, you have quality improvement. We're removing that human operator, human variable out of the process. So you're going to have if you have seals and gaskets, well, guess what? They're going to be able to seal. We're not going to have to worry about, oh, this particular operator cut a little bit into this part, so this part is rejected. You're going to reduce your rejection rate on your components that you're processing and molding. So there's your quality improvement. Again, human operator variable. Is it still there? Yes, we do have an operator at the machine, but we don't have the variability that comes with many people deflashing the parts by hand. I mean, some people are having a good day today, some people are having a bad day today. It changes. So the point being is, we have a machine, we're inputting a part number, they hit enter, they run it time and time again. It's consistent. Next, one of the major advantages, in my opinion, above all else, whether you're processing rubber or elastomers or plastics or even metals, cryogenic deflashing is non-abrasive. It's not going to change the surface finish of the part. You're not going to have, like if you were to use like a vibratory deflashing process or something like that, where you have a ceramic media, the surface finish is going to be changed. It's going to be dulled. Cryogenic deflashing is not going to change the surface finish. It's simply going to remove the flash, and that is all. And you're maintaining part integrity. We don't go below the glass transition point of the material. We're not going to induce stresses in the parts that we're deflashing. At the end of the day, we simply want to deflash. We simply want to freeze only the flash. We don't want to freeze the entire part throughout, because that's going to induce stresses. So you're able to maintain part integrity with this process. To the right, you can see this is a silicone part, a green one, and it's got, parting line flash running down the side, and then where one of the cores comes out, you've got flash that, comes off of that. And then we have it after deflashing. You can see the surface finish isn't changed. It's still got that, under light, you still have that brightness. It's still got that glossy look to it. So again, simply removing the flash, not removing, any surface material or changing the surface finish of the part. Next, cryogenic deflashing equipment. So I wanted to show you guys the equipment that we use in particular here at Nitrofreeze. The majority of what we do, although we do have a cryogenic tumbler, we use the SSB16. It's a cryogenic deflashing piece of equipment. It is a media blaster machine. We have a 1.6 cubic foot basket that we load parts into and process them. And we have the onboard computer. So you can see in the picture, the little keyboard, that's where you input your part number. And you also have one of the nice advantages of that, just above that keyboard is the monitor. So you can see, the different process parameters. But we also have a barcode reader. So if you have your part numbers on a box and you save them in the machine, you can literally scan the box and it will recall the part number so that the operator doesn't even have to input it. It's just a simple scan. Scan it, and then it'll populate on the screen and hit enter when you're ready to run. So we're using liquid nitrogen as a refrigerant. In cryogenic tumbling, I've also seen dry ice pellets used as a refrigerant. If liquid nitrogen isn't available, I mean, in the United States and in North America in general, cryogenic dioxide, solid CO2 has increased roughly, 2 200% in the past 5 years. So, you know, liquid nitrogen is extracted, it's recycled essentially, it's extracted from the Earth's atmosphere, and it's readily available, and it's, you know, very low cost. So that's what's being pumped into the machine. Next, you have gaseous nitrogen, okay? Or you can run the media blasting function with shop air. Problem with shop air is, you know, you're introducing the potential for contamination. I mean, you know, compressed air can have, you know, if you have an air compressor that's old, there's the potential to subject, you know, different fluids, whether it be like, you know, some kind of lubricating oil for the gears and the pump. So there's that issue. So what we like to do is we have a very large nitrogen bulk tank in the back. That's where our liquid nitrogen refrigerant is. It's piped in via cryogenically, you know, a cryogenic grade pipe. So it's heavily insulated, so there's no waste. And we have a separator, or no, we have this system that essentially flashes the liquid nitrogen into gaseous nitrogen. And what happens there is that way you don't have, you know, the issue with the shop air, but also the beauty of this process is, you know, people tend to get scared when they hear liquid nitrogen because liquid nitrogen naturally occurs at negative 320 degrees Fahrenheit. This process, we're flashing the liquid nitrogen into gaseous nitrogen. So the reality is liquid nitrogen is never coming into contact with the parts. It's simply a gaseous nitrogen atmosphere. So that's, you know, inside that chamber where the parts are being processed and the flash removed. Next, we have Swaco media and flash separator, and I'll show you that in a couple slides. But it's a small machine. You know, in our facility here, we have 4 of them, and they run, you know, all day, every day for an 8-hour shift, and very efficient machine, very easy to fix. Parts are commonly available, and it does a very efficient job of removing, you know, flash from, you know, plastic, elastomeric, and rubber parts. I wanted to show you some different deflashing samples. So over here, we have on the left a silicone, you know, gray silicone gasket. It's got both flash on the interior of the exterior. You know, a part like this is very good for the media blasting process in particular, just because, you know, it's very difficult to remove the flash on the interior of the part with using a cryogenic tumbling process. Next we have, this one is also a silicone component, and it's actually it's rectangular in design, and it has a window that goes through it, and where the core comes out you have flash, and it was pretty extensive. This process, for the most part, you could tumble it and you could media blast it. Both would work. But in particular, again, we found that our most efficient process was with the cryogenic media blast deflashing. Lastly, we have, this is a EPDM rubber part, and this has, you know, flash both on the interior and the exterior of the part. In the interior, you know, it's pretty significant, and that's where the core comes out. So, you know, with this gasket, I mean, the flash on the exterior wasn't that bad. It would be a great candidate for tumbling if it was simply external flash. But with the thickness of the flash where the core pin came out, this is where the cryogenic media blast deflashing process worked phenomenally well. Did a much more efficient job, and it was a rapid cycle. You know, the parts were able to tumble against one another and also have the media blast at them. Next, we have our cryogenic deflashing chamber. So I wanted to show you, how the parts, you can see parts in this basket here. That's what, again, when we're, creating the sample and running the parts, we want to cover the bottom of the basket at a minimum. That's a good way to start with the sample. And then, go up as needed. So, in terms of the machine, it's got a door. We open the door. The basket is, probably on a table. We have essentially a deflashing cell. Parts are on the table. They've been, put in a bin. They're put in the basket. It's brought over the machine. The door is open. The basket is put up and into the machine. And then, your process, your cool down, and then the process begins. So again, parts are tumbling in the basket. Basket is rotating so that the media blast function is able to equally cover all those parts and remove any residual molding flash. Next, we have the media separator. So this is one of the really cool things about this particular system. And pretty much any media blast deflashing system, from any manufacturer is going to have one of these. And it's doing multiple functions. So not only is it, filtering out any residual flash that is removed from the parts, it's also, filtering good media and bad media. Okay, so good media would be media that is not worn out and is still capable of deflashing parts and hasn't gotten smaller, in its size. So there's different screens in here. So some of the screen, basically your good media is going to funnel down to the second level, and so is the flash. And then, the flash ends up being very small because it's being blasted with a media and becomes very fine particulate, like almost like sand grains. And what happens is it falls through the next set of screens. And then we have if you look at the picture on the right-hand side, there is a black like box. That black like box is a waste basket, essentially. And what it is doing is removing, in there is where all your residual flash from molding operations that has been removed, that's where it ends up. And in addition, any bad media that's pretty much burnt out and not capable of fulfilling its purpose to remove flash ends up. If you look to the left-hand side, you have what we call the hopper, okay? And that is the media hopper. So good media that is, from the top of the machine, blasted down at the parts, it ends up, filtering itself down through the basket at the bottom, which is like screen-like in nature, so the media is able to filter out and fall out. Then there's at the bottom of the chamber, a hole that leads down to this separator. That media is then funneled into the hopper and then cycled back up to the throw wheel so that it continues to deflash the parts. Now, we're going to have a discussion on the, different, functions of deflashing. How are you, Srikanth?
Hi, Ryan. Thanks for a fantastic, let me say, a 101 combined with a 201 session on cryogenic deflashing. Let me introduce myself. Very good morning to you, taking your time off in the morning. Let me introduce myself. I'm Srikanth. I hold a degree in engineering with a master's in management. And I run this company called Alfa, which is now 34 years old, making parts for the automotive. So just before we started the session, I did mention to you that I have a bit of surprise for you. So my, let me say, tryst or brush with cryogenic deflashing started about the same time that you started as an intern in your company. So that's way back in 2001, 2002, where at a cost of about $4,000, we built a proof of concept. In India, we built a proof of concept and it did work. So that was to understand the processes, to understand the system, and to understand whether it really works or not. So that's the way Alfa Rubber has been associated with cryo deflashing. But of course, we got our own big equipment in 2010, almost 10 years later on. So that's the way it is. So let me ask you a question. You did talk about everywhere you use the word services. So how does the industry work? You have manufacturers coming to you with parts and you give it back to them after deflashing?
This is an excellent question, and what you just said is exactly right. So we have customers all over the country in the United States essentially sending in boxes of parts, whether it be pallets, or simply boxes, and then they send them in. We process them. We do a quick turn on them. So we turn the parts around from the time they get shipped in to the time they ship out. It's 2 business days after receipt. If the parts are needed on an expedite, we also offer same day and next day service.
So let me put this in the Indian context. In India, we have our OE customers, the automotive manufacturers, leading the pack in trying to spec cryo deflashing equipment as part of the processes which they would like the rubber vendors to have. So they slowly started asking questions whether the manufacturer is got this capability or not. Whether it is actually used for his part or not is a different question, but they're asking whether the manufacturer has got the capability or not. If you look at it, we are a couple of, maybe say 10, 15 years back from the advancement that you are in, both in terms of compounding as a service and deflashing as a service, or even PTFE coating as a service. We prefer in our country to have all these under the same roof as a manufacturer. So that's the way it works currently. So we have pretty much, I think there are 2 to 3 manufacturers of the equipment who have done a bit of indigenization from what is available abroad. But most of the people who own the equipment are either imported from Europe, or let's say the Americas, or let's say the Taiwan or the Chinese. So that is the way the trend for the equipment goes, because the equipment is pretty much a bit expensive for a small time manufacturer, and at the same time the utilization, like you correctly mentioned, it's provided as a service, so your equipment runs 24/7 every shift. So for us, whether we have enough bucket of parts to run the equipment for maximum utilization or not still remains the question.
Right.
In this process, I mean, whether you do it as a service or whether we do it in-house, what would you recommend, or what would you say is an allowable rejection percentage when someone throws a bunch of new parts at you, where you do a trial and error? How do you explain to him that the first couple of runs that you do may or may not get deflashed, or the part may get damaged? So how do you handle that?
So great question. Ideally, what we always tell our customers is send me samples. I will do some free processing on them. And what I end up doing is I run, I send them back several samples. So I'll run, their parts to several different processes, ideally trying to achieve the same thing. Because some customers are like, you know what, a little flash left on it is acceptable. Other customers are like, it's got to be under this tolerance. So we have inspection equipment, which you can see behind me, that's capable of doing that. So what I always tell them is like, look, there is the potential for breakage. I'm very upfront with them on the process. And I tell them that you need to understand that these parts are simply for an experiment, and that's to develop a process that there is the potential for breakage, that, there is the potential that not all the flash might be removed. But what I always try to do is, pre-frame it and look at the parts before they come in. So I try to get, pictures of the parts and understand, okay, and show me a good part so I have a reference point, but in terms of rejection rate, when it comes to, running it every day, I mean, we do different rates of inspection. Some customers require 100% inspection. Other, customers have a certain AQL that they want to process the parts to. I think it's variable on which process you're running. in cryogenic tumbling because the parts are really, you can get them humming going along. I think, somewhere around 10 to 20% is probably what you're looking at. If you're running rubber or silicone in those processes, I mean, it's very common that you're going to have breakage. It's just, that's the nature of that process. With the blast media deflashing, I find that, we're able to achieve in terms of breakage, it's very rare that we see breakage in that process just because the parts are only tumbling at, say, 10 revolutions per minute. So the tumbling isn't doing it, the work as much as the media is blasting it down at the parts. So with a process like that, I mean, I easily see with the cryogenic media blasting, if you optimize the right process parameters, there's no reason you couldn't get under around 1 to 2% reject rate. It's achievable.
That's very good. On the, I think one point you had missed in the presentation, which is part of the 101 series, is if you have a basket which is 1.6 cubic feet, what will be the fill factor that you would recommend? I think the norm is 1/3 or what?
Yeah, roughly a third. I would say a third. But again, that is dependent. For the bulk of what we do, it is a third of the basket, I think is a good rule of thumb. And that ranges, because some parts have a 4 cubic foot basket. Ours has a 1.6. So I think a third from the bottom is ideally where you want to try with a cryogenic media blaster. When you go so high, if you were to try and put all those parts in that basket, you're not going to get the tumbling effect you need, and you're not going to get the media to get all the way down to the bottom of those parts. Ideally, you want your parts to be able to tumble against one another, and you want the media to be able to hit each and every one of them. It's very important.
From your experience so far in treating hundreds of millions of parts, as well as across a broad range of polymers and rubber, is there any elastomer that cannot be processed in this? I mean, that's the exception question, because if you have given a broad range saying that polymers is from so-and-so temperature to so-and-so temperature, elastomers, which I assume you mean is rubber, the commonly used word, is from so-and-so to so-and-so, and then you talk about metals as well. Is there any elastomer that cannot be processed in this cryogenic flashing? I think that would be the exception question, easier to answer rather than trying to say that,
No, that's a fair question. And the reality is, in my experience, we haven't had that issue. I mean, I haven't found. What I can say is, with parts that are, and this is more not so much elastomers as much as it is, like different durometers of parts. What I've found is low durometers, like say 0, or like when you're really low on like 10 durometer and stuff like that, they're almost too flimsy to process. I find the sweet spot, to be like it's got to be at least 20 durometer, but 30 and up is good. No problems there, but 20 can be tricky. But like a 10 durometer part or a 5 durometer part, very difficult to process. That's been our experience.
So you mean to say your all orders of nitrile rubber, carboxylated, hydrogenated nitrile, the entire order is processed. All orders of FKM, FFKM, etc. is processed. Various varieties of silicon, fluorosilicon is processed. But uniformly across, low durometers are difficult to process is your comment. Let me also ask, in our experience, we have also had this issue of O-rings, which have very thin cross section and a large diameter. Processing them, the rubbing action tends to give us cut O-rings at the end of the process. So have you had that experience? What would your comment be?
How big?
So let's assume that you have an O-ring which is an inch in diameter, to looking at O-rings which are 3-4 inches in diameter with 2 mm cross section. So we find that the O-rings are too flimsy, irrespective of the hardness, that they get cut. So
Yeah. So it's funny you say that because we have had issues like that has come into, you know, it does cut. I've seen parts that are just so thin in cross section that, I mean, you can literally, the flash almost blends in with the part
yes,
geometry. So in a case like that, you know, what you're going to do is when you're sampling it, you're going to want to run, you know, this is one of those very rare cases where you're going to process at very low process parameters to start, you know, and there's parts and it's quite, it could be possible that a part like that won't yield itself to the process. You know what I mean? You
right.
can, it is possible. I've seen parts where, or there's, you know, there are where we're deflashing some of them, or there is a significant reject level, and then it's like going back to the customer and saying, hey, we can do it, but you're going to experience a much more significant than usual fallout rate, and is that acceptable? You know, I mean, that can happen. But yes, I've seen there are unfortunately, like anything, there are parts that just will not yield it themselves to this process. And this is where, you know, you know what, this is where why there's so many different deflashing processes out there. But what I have found is for the bulk of rubber parts, you know, elastomers and polymers, you know, if you're going to, you know, if you've got flash both on the exterior and the interior of the process, you know, parts, and you're trying to remove it, and you're looking at, you know, the flash isn't terribly thick, and you're looking for a repeatable process, this is the way to go. That's been my experience.
So going back to your presentation, you showed an EPDM part, which had flash on the ID and flash on the OD as well. Now, does the thickness of the part play a role in removing the ID flash, because the blasting media has to reach to the inside? Let's assume that the part is an inch thick. So it's a bush with an OD of an inch and the ID is about a quarter inch or so.
Okay.
And so the ID is where the core pin comes out. So the height of the bush is about an inch or so. So the flash you find is on the inside, either on the top or on the middle, depending on the configuration of the bush. So do you think the media will go in, penetrate to that level of the part and deflash it, or what happens?
So with a part like that, what you're going to find is it will deflash it. If it's a cryogenic tumbler, probably not going to do it. That's reality. With the media blasting, it will. With something like that, you know, especially with the dimensions of the part, that's a part where, you know, it's going to lend it. It's one of those rare off cases where you're going to not run. You would start, instead of like with a 15 thousandths media, you would start with a 20. And the reality is on a part like that, because it's a bulky, durable part, you're probably going to end up running it with 30 thousandths media. The other thing you're going to have to do is you're going to have to make sure your batch size is, you're not going to be able to go that third of the way. You know what I mean? And the
It has to be
other,
a smaller size.
correct. And the other thing is the cycle's probably going to be longer than usual. You know, it probably, you know, let's say you had a 10-minute set, you're probably going to be looking at a 15-minute set on a part like this. You know what I mean?
So if you are got it in your management system to cut out the labor, which does the deflashing, I think then what you're compromising here is a bit of a longer cycle time, but the parts will get deflashed, is what you're saying.
Yeah, I mean, you know, and that's largely where the economics come into play on this. I mean, you know, there's parts that we can process. You know, our limitations are basket size, and you know, I mean, we do a lot of very critical tolerance parts that are very extreme in nature. I mean, we honestly advertise the fact that we process our customers' worst parts here, and even beyond that, and I'll tell you why. We have competitors that there are deflashing houses elsewhere in the country. Okay. There's some in California. There's some in Minnesota, Wisconsin, and Ohio. So, you know, where the manufacturing is in the country. And what we found is a lot of people, you know, who are based in that area will run parts with these companies, and then when they get something they can't do, they'll ship it the extra 2 days UPS to get it here and pay, you know, and they'll pay for that to get that done. So, you know, we do a lot of high value stuff. So it's like a matter of, you know, sometimes it's like the customer looks at the total cost and it's just like, okay, well, we're going to make a little less money on this, but the part is going to be deflashed and our reject rate isn't going to be bad and it's worth it to them, you know? So that's just how it is.
So we did discuss right now about a bit on the size of the part, the geometry, and what works. Coming to the media, in India, the media is imported 90% of the time. We don't have manufacturers of the media here in India. So one question that will always be in the manager's mind is, what would be the reuse criteria for the media? How many times can the media be reused before you really find out that it's broken down or thrown out? What would be your experience on this rather than a thumb rule? What has been your experience?
Great question. So if you were running an 8-hour shift a day, okay, you know, 5 days a week, we find that cryogenic polycarbonate grade media, you know, with the average settings, so like let's just say we were running like a 15,000 RPM throw wheel, because that's, you know, the rate at which the media is getting blasted at the parts. If, you know, that's on the lower side, your media is going to last longer. That's going to largely dictate how long your media lasts. That and temperature. What temperatures are you processing at? You know, if you're running silicone, stuff's going to break down faster. And it's also dependent on what it's deflashing. You know, again, we do polymers, elastomers, and rubbers, you know. So what we're finding is, you know, plastic part, hard surface, media is going to last shorter time. I think a good rule of thumb is, you know, you're buying it, I think it's like, I want to say it's like 50-pound boxes or something like that. Yeah.
Yes,
so, something like that. I mean, if you're running it every day, those boxes should last at least, you know, 20 days a month roughly. You should have, there's no reason that shouldn't last at least a month, but I can say I've seen as long as 3 months.
Right.
You know,
so you're saying that depends on what it deflashes and the temperature it's used.
Correct. It's going to be temperature and it's going to be what you're deflashing. That's going to dictate that. But a month to 3 months is a good range.
So in your presentation, you did touch about how to go about setting the time. You start with the minimum time and increase. You start about the media. You start with the smaller size or the average size rather than the larger sizes. Then you talked about the RPM. So if you look at polymer temperatures, you know, we get some of us have imported these machines. We got user manuals without a starting point temperature for any polymer, right? When I say polymer, I will confine myself to the elastomer part of it. So how does the TG of the rubber help you as a thumb rule to fix the starting point temperature for this process?
So with something like that, you know, again, it's a wide range of temperatures, you know, and what I found is we will specifically ask our customers for material data sheets before we process parts. We make sure we know what the glass transition point is. And if it's not listed, we'll go to the manufacturer, we'll have the customer go to the manufacturer and ask. I mean, there's certain plastics that I've been told there really isn't a glass transition temperature. And it's like, well, okay. So, I mean, this is one of those kind of situations where you have trial and error. But I think, you know, again, there's good guiding practices, you know, like a silicone, you're looking at, you know, for example, just a silicone, -150 to -190. You're going to be somewhere in that range. And more likely than not, you're probably going to be somewhere between -170 and -180. But I think, you know, you can start low and go high. But it's usually in the middle of those ranges where we find the best deflashing, processes, plastics again. And plastics is a wider range, but a lot of what we do is negative 40 to like negative 80 degrees Fahrenheit. It's somewhere in that range.
So you mean to say that the glass transition would be the absolute maximum of what you catch, or what will it be?
Say that again?
Let's assume that you have a nitrile rubber where the TG is minus 40 C,
Okay.
minus 45 C. So on the process part of it, where would you start?
So something like that, I'd probably start about 10 degrees cool, 10 degrees warmer. So like, let's say, you know what I mean?
Minus 30.
Well, in Celsius, it probably would be closer to like 5 degrees. If it was Fahrenheit, it would be 10 degrees. Celsius, you're probably about 5 degrees warmer, than the glass.
So have you had customers come back to you after the process saying that the microcrystalline structure was affected, and hence either the tensile or the elongation got affected on the part after the process? Were there any issues, technical issues on the physical properties raised?
We have not. We've actually, even for some customers, we'll literally do samples where we'll just take pads of material and we'll put them in the basket, and we will, subject them to the temperature we're going to be running at, roughly going to be running at, or a rate we'll run like one at, and literally not blast media at it, but just subject it for say 30 minutes at negative 150 or negative 160 and negative 170, so that they're able to go do that testing. We haven't had people come back and say, hey, there is now issue with the parts in terms of properties being detrimentally affected. No.
You haven't had.
No.
So in your opinion, what was the most complicated part you ever did in the last 15 years?
Oh man. So this is more, this is a plastic part. We did quite a bit of peak surgical grade implantable cages that go in the spine, and they have all these little pyramids on them, and it's a molded blank, and then it's machined. So it's like kind of like, looks like this, and it's got all these pyramids on top, and on all those pyramids there's burrs. These things would be loaded with burrs, and this is more it's a molded part, so it had parting line flash, but it also had secondary machining operation where it had that. So that was a significant, that was a challenging part, because it was an extended cycle time, because we don't want this material breaking off and going into somebody's back. That's that's a huge issue. So we do a lot of medical device here in the United States. Some of the other parts we've done we've done some very interesting silicone parts that were basically like cylindrical in nature, and they had all these different cross sections and cross holes that, there was flash right, very difficult to reach, and the reality is the core pins, where those pins all met, there was flash, and when they wore, as the tool got older, you had more, we had to extend the cycle time, and we also had to reduce the batch size, so that's something else you have to keep in, be aware of, is that, as the tools wear and as they age and as they're processed more, the flash can get more significant, and the process can change. But if you do your basic maintenance on your tooling and such, you shouldn't. These issues can be, minimized as time progresses.
So you use the word flash here. So when we're talking about parts in that sense, at the end of the process, I suppose minimum flash will remain, and that would be as per certain standards. Am I right, or there would be no flash?
So this is a good question. typically there's a tolerance, and it's funny because, I mean, ideally we're running the same process to remove burrs, and quite often we get, specifications on part drawings that says no burrs. Well, that's fine, but that's at what, is that a visual? That would be at a visual magnification. Well, that's no problem, but if you want me to look at, I have had customers come in and say, well, I need to look at that at, 20x under a microscope. Well, if we look at that at 20x, it's not going to be burr free, but with flash, typically you've got a tolerance. I mean, we just ran a part, I just got a sample in the other day. They had a 2/1000th of an inch tolerance on the flash. And we were able to get, down to like, for the most part, 1 thou across the part, but also in certain spots, I mean, it was completely abraded, so it differs. It differs part to part, but typically on flash, I mean, we're trying to make a part for manufacturability. To achieve no flash is very, very difficult to do.
So that was good. And so if you talk about flash like this, then a lot of people have this mistaken concept that only Tatrum molds cannot be used, and only molds which are suitable for so-called mechanical deflashing. That means there is no flash line are suitable for cryogenic. So, but in our experience, we have put both kinds of parts, parts without a Tatrum line, and we have also put parts with a Tatrum, and we don't find any difference. In fact, if the machine breaks down and you have a mold without a Tatrum line, then you're stuck with deflashing manually. It's a mess. So what would be your experience be?
So with, we've done parts both ways. Absolutely. It's gone both ways. The majority of what we do does not have a tear trim. And what we find is, with parts with tear trim, what ends up happening is that can create its own issues, where you end up with all this flash particulate, and in a tumbler in particular with all that tear trim, I mean, that can almost start to impede your deflashing. Especially in our process with the media blasting, that tear trim, if it's thick enough, isn't going to get battered down and turn into fine particulate. So the reality is the best parts almost don't even have tear trim. That's, I think, if you're using media blasting or you're using a process, I think that, what you're almost, if you're gonna deflash the parts that have tear trim, just rip the tear trim off before you put them in and save yourself the hassle or the complication of having to, have that impede your process. You're better off doing the tear trim beforehand, before processing the parts.
So that's precisely what we do internally. So before I think I should have, I think between your 101, 201 first level and second level on the cryo process and the discussion, I think we have given a decent overview on the entire process. But as a hand-holding method, I did check your website before this session.
Oh, no worries.
So you have a lot of blogs on it which throw some light on the processes. So what would be some starting point literature that you recommend for people to get into the process? Of course, they can do this webinar on demand and learn from it as well. With your voiceover, I think that's the best that I have listened to in quite some time. But are there any materials available that people can take a look at and create training materials out of it for their own staff before they use the machinery and things like that? Because what we get are user manuals telling use this temperature controller, use this, use that, but nothing like the way you have cogently put it together. I mean, let me be very frank.
So it's funny you asked that. There's a couple places as far as books, I don't know of any, but what I can tell you is a couple good places to look. There's the Cryogenic Society of America. That's a good spot, and then there's a couple good websites out there. about cryogenic deflashing that have different, articles about it. There's been articles published. I mean, you can do a simple Google search, but I mean, then you get all kinds of different results. One thing I would recommend is any of the liquid nitrogen suppliers. So, and I don't know what suppliers there are in India, but what I can tell you is that, for example, here in the United States, we have Air Products and Chemicals, we have Air Liquide, we have Air Gas. Their websites tend to have a lot of very good case studies, and they even have, some of them have manuals on the deflashing, on the deflashing process, like a basics overview of deflashing, and they'll even give you some information as to set points and such as to where you process the parts. What kind of, like, for example, like a peak, you might run it, say, -60 degrees Fahrenheit. So that is, those are recommendations I would have. Cryogenic Society America, and going direct to the liquid nitrogen suppliers themselves.
So the liquid nitrogen suppliers in India would be Inox and such kind of people. So, but as I think the industry has not progressively accepted this in that sense, I doubt whether we would have case studies put up. But one interesting thing is your mold deblasting that you had shown in the first stage, the mold cleaning process. That is prevalent in our country as a service. So there are people who come with those machines and with the dry ice, and they don't lug around LN2, but they lug around dry ice, and they do the blasting, and they clean the tools. Specifically, the tire industry adopts this, and molders like us who have large molds with hoses, molded hoses and things like that, where there are corners which cannot be reached. I think that is a way to do. Every 2 months or so, we get the molds cleaned using that process. So I think if this conversation is coming to an end, let me thank our viewers for giving us this opportunity for the chat and patiently listening to the discussion. And obviously a fantastic 101 from Ryan Taylor from the Cryogenic Institute. Thank you, Ryan, and over to you, Param.
Thank you, Srikanth. Appreciate it. Thank you for your time.
Thank you, Srikanth. Thank you very much. Ryan, would you like to give any final remarks to the audience?
Yeah, so I would say, ultimately cryogenic deflashing is, an efficient means to remove molding flash from rubber molded parts. It's gonna, and it takes the human variable out of it, and there's a significant savings in terms of time and cost. And that's what I got.
Okay, thank you, Ryan. Thank you, Mr. Srikanth. Thank you very much for being part of this Rubber Industry Tech Talk, focusing on the technology trends and practices in deflashing of rubber parts. Guys, it's the end of this episode today. Thank you all for joining, and you can watch this whole session on YouTube at the Technobiz channel. And if you need any assistance from Technobiz, you know how to reach me. I think most of you have information of my contact information. Feel free to contact me. I see you next episode. Thank you all for joining this session.